So before I start, just a quick survey. How many of you have taken the computer games class? Comfort. 521. 521. Computer games. Okay, I see. So for the people who have taken the course, I guess there's quite a few overlapping of what I'm going to talk about today. So just bear with me. There will be something new, but not at the beginning. So today's talk, it means to be more introductive, an introduction to video game AI, and it's also very I want to open to all the discussion. So feel free to pose questions or express yourself when, if you want. So a little bit about myself. My name is Lancer. I'm the associate programmer of GameDev McGill. I'm really interested in AI for a while because it's a very interesting topic that involves not just the technical part, but also make you question about how would you program AI that really simulates human in real life, or you don't know if you really want to do that. But there's a lot of questions that you want to ask yourself when you're doing all these kind of things. So before I go to more open questions, I want to first talk about. So the first question I want to ask is, what is considered AI in video games? Which always comes in a lot of forms. So first, start from the very beginning. We have arcade games like Pac-Man or space shooters. Those are the AI first implemented by a human that's meant to entertain people or to generate obstacles before preventing players from reaching the goal. And then we have also some other games like simulations, like Sims, or some other simulators to simply trying to summarize, generate information or simulate things in real life to see how things grows, and also to predict the future, see what's going to happen. For example, like the ecosystem simulator. And we have a real-time strategies, which is more popular in 20s, in beginning 2000 years, where you have Warcraft, and so you want to compete with computer in these kind of strategy games. Or also we have chess-like games, like here I've showed the picture of Fire Emblems, which you can basically play all the characters with different abilities around a giant chessboard-like map, something like that. And then afterwards, we also have action games, and first-person shooter, and even the horror games. We have some very famous, like Alien, that you might play before. So here's the picture. It's not really an AI, but I don't know if any one of you recognize her as one of the demo on PS4 in 2016 or something like that. I don't know if anyone can recognize, but if you can, feel free to say the name or post in the chat. yeah. Yes, it's from the PT, which is really a scary. It's a scary demo. It's not a game per se, but it was once a nightmare for me. So first, AI 101 first. So I wanna introduce the concept called autonomous agent. So what is autonomous agent? Here is the a textbook definition. Basically, it's a system situated within and a part of an environment that senses the environment and acts on it over time in pursuit of its own agenda and so as to affect what it senses in the future. So in a simple way, autonomous agents should be able to handle themselves once they are granted free to move around. So, and they can obviously handle certain situations that happens dynamically, or also follow certain logical behaviors. For example, a fox should behave like a fox, or any other animal should also behave like other animals. So you won't you won't be like have a rabbit that really doing things like fox, like trying to eat, for example, a tiger trying to eat something that they shouldn't eat. So that's not really what is supposed to happen. So to actually build an autonomous agent, usually like three things are what we consider in games. So the first one is called the action selections. Basically, it's like which action you will choose to take under certain conditions and the situations. And then the second one is steering, which is after you make the selection, how are you going to reach that location or uh, execute action. And the local motion, which it's sort of like a motion, but the reason why it's separated is being separated from steering is that imagine two different kinds animals going towards one location at the same time, even though they're doing the same behavior, same motion to move forward, but the way the animation played or the trace that it's going to follow will be different. For example, the rabbit will probably go directly towards the location, but if you have something flying around, it's probably have some wavering kind of motion to going towards the location. But essentially, they have the same goal to reach the destination, but the local motion, which allows you to have the flexibility to basically move around with different animations. So what is a steering behavior? It's a physics-based, and it's a really easy to implement, and it's basically what you learn from physics class about velocity and object motions implemented in code. So to give you a sense of what it means, first let's see we have like a seek and a flee motions, which seek, as what it means, is going to seek towards the desired location. So imagine we have an agent that has current velocities, and we also have an object that we want to move towards. So we will have a desired velocity, which essentially is just the vector using the location of the object subtract the current location to get this vector. So then what forces or what speed it needs to have to be able to change from the current velocity to the desired velocity, and basically just do the difference between them, so you will get the change, which is in that direction that you want to apply to their current agent, so that it will go towards, in the end, it will go towards this object it wants to go to. So flee is the opposite of seek. So basically, the desired velocity will be the opposite of the desired velocity here. So we'll go in the opposite direction. So the change will be, if you can imagine, will be the change, the difference between the current velocity and the desired velocity, which is in the opposite way. So we'll be this enormous vector that pushing the agent to the opposite direction. So above on that, we have some other also very interesting behavior like arrival and wander. So arrive basically means that we stop at the location gracefully. So the way we do that is under certain regions, we will start to slow down. And so the amount of the velocity that we want to decrease is proportional, inversely proportional to the distance to the object, right? So the speed, it basically is the distance to the target divided by the time. So the time is something we can define ourselves, which means we want to slow down rapidly or slow down more slowly, which means we can give a range of time and then we use the distance to the target to determine the speed variable. We can basically determine, okay, then that's the desired velocity that we want to have at a certain moment for our agent. Then we can basically, the rest of them is just the same as the seek. So we can seek to the location with desired speed. So, and to implement wander, it's another thing that you want to have for your agent. For example, you want a agent to kind of like roaming around. So the way to do that, maybe you can imagine, is just to add a randomness to above the seek mechanism, so that you can seek to an offset of this direction each time. And the more this wander force it is, which means the offset will be smaller each time you do the adjustment. So it will eventually still going forward with a very little displacement, but with a strong wander force, which means you will likely to turn around and to do this going on in circles or doing more doing a behavior that has like more randomness without a general direction that it's heading to. And above on that, we also have pursuit and evade, which it's basically calculate a distance, a target position in the future with another autonomous agent moving in action. So you basically predict the location in the future so that you can pursue, basically seek to the future location instead of the current location, so that in the game, it will behave like it's going towards the place you're going, that you're going. So instead of just chasing to the location you are currently at right now, which will never, which the agent will never be able to reach because you're constantly moving. So just having this little modification will actually make your AI look much smarter than the one that just dumbly going towards the location that you were at in the previous time. So evade is basically the opposite of pursuit. So it's just the difference in the direction that you want to change. And then another one to talk about is the group behavior, which is something that you can do called separation, cohesion, and alignment. So the separation basically is something that the agent will try to push in this radius. The agent will try to push all the other agents in this environment, so that it will try to invade from all of them. And the cohesion on the other side is trying to find average position, basically the center of all the agents. So it will try to steer in towards that location. And alignment basically is trying to, Okay. Oh, sorry about the noise. So here, the alignment is just trying to basically find a general direction, so that eventually it will all the agents in this area will trying to steer around the same uh, at the same direction. So to betterly okay, so to better demonstrate the effect. So here I have a little demo about what it actually means by arrive, for example here. So this agent will try to steer and then eventually stop at the location that I'm trying to point. So also here I have, for example, free, which means we're trying to free steer away from what I'm trying to point. And here's the longer. Basically, it's adding an offset to the steering direction each time. So you don't actually see the circles, but just by looking at the agent, it is actually trying to kind of like wander around in the in the randomness with the randomness here. And then to show that a group behavior, so for group behavior, it's often used all together to produce a behavior that is called flocking. So flocking essentially is what I'm showing here. You can see, so all these small agents, they are following sort of rules that defined by the separation cohesion alignments. So they're trying to align with each other, so they will all follow a general directions. But at the same time, they're also trying to separate them each other and pulling them all together. So each time they are separating themselves to a certain distance, but they also have this rule to cohere, so that they will try to do this kind of behavior that uh, always staying all together, not too far, not too close. But at the same time, they're also trying to invade this bigger agent, so that it will be a certain distance whenever this agent is trying to head. So basically, that's an interesting fact that you can see you can produce with this kind of simple behavior. Uh, so under the very fundamental part, it's very simple, just simple physics with a definition that we can apply to each agent, but uh, building on building on each other, they can actually produce some very interesting behavior, like the flocking behavior, which you can use to simulate fishes, like fish in the ocean, or to have like even you can use them to simulate people when they're trying to invade from danger, but they're also trying to form a group together or something like that. So any question on the steering behavior? Okay. So if I don't talk clearly, just let me know. So I'll repeat what I just said. So next part, it's about navigation. So so what is a navigation is about? So it basically means trying to navigate from one location to another. So essentially, it's a search problem when it's formalized. So you want to search a path from one location to another given a map or a graph in a simple way. So then when it comes to search problem and on the, for example, on the path, you want to find the shortest path from one location to the other, and we always come up with the Dijkstra's algorithm on the shortest path. So I think I think all of you should have heard of this, the algorithms, and just a quick recap on what it does. I'm going to use the annotate tool to basically show an example. So can you see what I draw here? Okay, so I'm just gonna quickly draw a graph. Okay, so okay, so for example, we want to find a path. I'll also give them wait. Okay. So for example, we want to find a path from 1 to 6. So how should we do that? So Dijkstra's algorithm will greatly find the shortest path that available from all the nodes. So to basically show that, first from the number 1, it will see that you only have 2 paths from 1 and 2. So basically it will 2 and 3. So 1 to 2 is 1. So and then basically it will try. It can only lead to 2 or 3, right? And then from there, what's the next next move to do? So from 2 to 5, there's -4, and from 1. So after you are here, so you're at 2 or 3, right? After 1, you can lead to 2 or 3. Here is 3. So from 2, where can you go? Then you can go to 4 with a cost of 4. And then from 3, you can go to number 4 or number 5 with the least cost, which is number 5. And go to 3 to 5 is 2, and 3 to 4 is 3. And then from 4 to 5, and then you can go to, from 4 you can go to 5, which is cost of 1. From 5 you can go to 6, which is cost of 1. From 4 you can go to 5, which is cost of 4. So basically what the Dijkstra's algorithm will do is, first it will try to select the least amount from number 1, so it will try to go here from 2. And then it will try to examine all the nodes that you can reach. So right now it's from 1 and 2. And then it will find that, okay, from 2 to 4 is at cost of 4, but from 1 to 3 is at cost of 2. So it will instead choose this number 3 as its next node to search. So and then reaching the 3 now, it will trying to compare 4, and its next from 3 can lead to 5 or 4 with 2 and 3 cost. And among all these costs, it will try to find the least amount, which is number 2. So it will try to reach this 5. And now the consideration becomes this 4, 5, and still this 3. Oh, sorry. So here. So considering these options, the least amount of the edge that you can do is this 1. So you start from expanding this 5 again, so you will reach the number 6. And once you reach the destination, which means you already find a path from the start to the end, then you immediately return so that you will find the shortest path from 1 to 6. And you don't have to consider the rest of the path. And this also works even though you have something that even though you have something like if you have a path that's like beginning is very small, weight is very small, but in the end you have something really big, like you're trying to consider this one path, for example, and then you think, okay, it's a good way to go here, but then you reach this very big weight cost of 4. So in the end, so this algorithm will not just stick to this path anymore. So we'll actually try to find a new path starting from the start point to this 2. So if you find something like very hard, considering this path, if you find something like really big 6, and then it will immediately give up because 6 is even worse than this 4. So we'll try to consider another path leading to this 3, and eventually it will always guarantee to find the shortest path among all these graphs. So basically, this is a way for you to actually reach this to reach the destination. But actually, you might realize the problem is it's actually expanding a lot unuseful path that essentially is not the optimal solution that you want. So a quick demo for that is that is I have this pathfinder that will show how the Dijkstra works in a grid-based game. So here, basically, it's how the Dijkstra will expand and search all the grid. So you see that it's basically will search all its neighbors and expand it in some ways that eventually it will find the destination and the halt. But it will find all but it will actually search all these grid that you don't actually have to do for the optimal, and it will actually cost a lot of time to compute all those things waste. So is there a better solution for this? Of course there is, which is an extension on the fundamental, the foundation of this Dijkstra algorithms. So, so to implement Dijkstra algorithms, basically what you need, the key part, if you have done it yourself in code, the key part is you will use a priority queue that will always guarantee to return the lowest cost to the next state, right? Because in the previous, we see that it will trying to return the lowest cost to the next vertex, despite of which path is actually following. So, which is a greedy method for that. So can we do better on that? So a way is to do it is called A-star pathfinding. So basically what it does is we can use something called a heuristic function to find information about how close we are to the location. So because right now with the Dijkstra, it's just calculating the cost from one path to another, right? So if the path is equivalent, maybe for example, this grid, you're going through basically each way, the cost is just one from one grid to another. So if the cost is the same, then it doesn't matter that which direction you should go. then the answer should always be the direction that the grid that makes you closer to the target is the grade that you want to go for next, despite of the cost. So that's the information this A star is including that will make this better because essentially it's a greedy best first search, which will always choose the best the options among all the available ones, so that as the result, with this the same graph and condition, if I use A star, then you'll see it will just directly go towards the destination without going to explore any other path here. So that's the improvements essentially from A star to this Dijkstra's algorithms. So what is a heuristic function, you may ask? So the heuristic function basically is an evaluation function that for you to approximate something that you cannot calculate in a short amount of time. So it gives you approximate result on something you want to calculate. Just for example, here the heuristic we added is how far are we to the destination. So to calculate this information, then this destination, the actual distance would be really hard to calculate because that's essentially what we want to find, which is the shortest distance from one target to another. But instead, can we just generally have a way that tell us in approximate time, like in an approximate value, how far away from one point to another? So the simplest way is, of course, the Euclidean distance. Basically, it's just a direct distance in 2D space from one point to another. And above on that, we can also, so here, if you go this direction, and of course, if you end up here, the distance from this point to destination is of course shorter than that, despite of if there are any obstacles in it. But if you go this direction, which means it's definitely not the right direction you want to go because the location afterwards will be further. So that's not the things you want to do. So basically this information is incorporated into this function. So with just the cost, so Gn here is the cost that we had in the Dijkstra's algorithms, and with its Hn is the heuristic, which means which is the distance function that tells me from one location to another. So all this together, if going this direction, I have a very low cost and also a smaller heuristic value, which means that's the direction I want to go for next. So I'm very likely to find my shortest path if I go through that direction. To better to visualize on that, if I have, for example, here I'm adding some obstacles. So here, the Dijkstra will essentially basically search all the math to find, because it will expand it will try to expand all the path, all the nodes without any preference on which one should go for. So with some preference, you will see that, okay, here, I might still search for some possible branches, but after reaching some certain level of distance, I actually have a better route that will outrun, which means it will get me closer to the target in some ways, based on this heuristic function. Then I will try to I'll go around this location, around this corner, and going this direct straight way, and then essentially find my path to the destination. So here you see that it basically it's not really running any other branches because the heuristic basically uh, tells you if you go that direction, you're guaranteed to get closer to any other options you have. So it doesn't expand any other path here. So yeah, that's the A star in action. Do you have any questions? Okay, great. Great. So the next thing I want to talk about. So there's a lot to cover. So it's the action selection part, which I mentioned in the previous about autonomous agent. You want to have action selection part that basically tells you what to do next. And then the one common way we used long time ago is called finite state machine, which you might know of. Basically, it's a set of states and a set of actions. And from one state to another, you have certain conditions, certain actions you can take to bring you to another state. And you will do something in this state. And then when some certain condition satisfies, and you will do another action to go to another state, and it will become a loop. So that even for an NPC, to design an NPC, you will have an NPC might have this loops to behave on their own without any interactions from outside world. Sorry, so that it will do everything on its own. But also you'll see the constraints in this state that they only have certain amount of states so that it will not handle all sorts of situations, just like when you're in a game, in your dialogue systems, you will always hear the NPC say the same thing over and over after a certain amount of variety on the dialogues. So it'll go back to the original thing it said to you, and it keep repeating that until no matter how many times you ask. So basically, that's like some like analogy for this state that it will not go beyond all these states. It will just it only lives within these states and keep repeating itself infinitely. And here is an inner UML diagram that you might want to use if you want to actually implement a finite state machine. So here, to quickly go over it, we have a NPC class. Basically, or have an update function which updates the finite state machine every time. So this finite state machine basically holds all sorts of states, and they can change states to certain state that it has. And then from there we have, so the finite state machine has current and previous and global state, which it can keep a track of what state is being on. And for each state, essentially it looks like a strategy pattern where you have this general state, general like abstract class that called state belongs to this NPC object, that you have certain method called enter, execute, and exit. And then you can go on and implement different kinds of states, basically, and then you define these three methods in each of your states. For example, when you want to enter, when we want to enter the cook state, and then you maybe want to tell the player or print a statement saying, okay, I'm going to cook. And in the execute method, you will try to do something that simulate the cook, or choose a recipe you want to cook, something like that. And in when the exit condition, it will be executed when you're changing the state from another. For example, you change the cook to eat until full, then the exit will be called before you enter to another state. So by implementing all these kind of states, you will have you will define what certain actions you want to go for under certain situations. So above on so like extension on that, you have a behavior tree. It's a more popular method than the finite state machine because it's more flexible. That essentially you can combine multiple behavior trees, and you can easily add and delete states or nodes in your behavior tree compared to the finite state machine. So essentially what it is it's a tree that it's also similar to a tree called decision tree. Basically help you make decisions. So you start from a root, and you go. They have certain different kinds of nodes that help you decide which node to which branch to go to next. So this controller nodes basically is the intermediate nodes that in the tree, and the execution node is the leaf node that basically represent all the tasks you want to do, like attack players or wait or do some animation, something like that. That will be in your execution node. So the selector node. So for controller nodes, you have two kinds of nodes. One is called a selector node. Basically, it will find the first child that does not fail. So basically, essentially, it's like a or operator. So either one of them succeed, you will trying to execute it and return immediately. So it will select something from a set. And then you have a sequence node. Basically, it will execute all the children under this node in an order from left to right, and return if one of them is not succeeded. To show it in the actual graph, so this is Unreal Engine behavior tree. So this is one of the AI behavior I made previously. So here, what I want to show is from this root, first it will have a selector. First, it will have a precondition called is game paused. So if the game is not paused, then it will go to a selector, which will trying to find the first node that is not executed successfully. Will try to execute the node that is basically satisfy the condition. So here, it will trying to execute this node, but I have a precondition called is player is being attacked, which is false if it's not being attacked. So it will goes to this condition, and so here it will be return a false. So it will go to basically two of these nodes. One of them succeed and one of them not. So it will try to find it will go to the first one that successfully executed and go to the branch of that node. So here, to better see it. So trying to go this direction. And then it will trying to basically examine all the conditions from left to right to see which one satisfies. So here is player detected. Basically, will return true if if a player is being spotted by the enemies. But if not, basically I will go to this logic that essentially I want just to move to a patrol location or wander around. So here it will be executed in a sequence manner. So and then first we're trying to move to, so trying to execute it in 1, 2, and 3 in this manner. We're trying to execute this, move to a certain location, and if allowing the patrol, which is another switch, and then we'll try to execute this node. We're trying to execute this node, and afterwards it will try to wait for 5 seconds. So what it does is the enemy will try to go. So this agent will try to go this location, and will try to wait for 5 seconds. and go to the next location, wait for 5 seconds, and then go to the next location in a random manner. So here, that's essentially it's wandering mechanics. And if the player is being detected, which means it will go to this branch, and this branch will not be executed. And so in this branch, I will first move to an actor, and then I will try to rotate towards the actor, and then I have more logic to see if I'm at a location what I want to do afterwards. So essentially here is the logic for attack. And by arranging these things from left to right in different order, you will see you can actually incorporate priorities in your behavior trees. And it's actually more flexible than the finite state machine because you cannot really do these kind of moving around things in your actual finite state machine than a behavior tree. And the last thing I want to talk about is is, is another thing called desirability. So imagine so here's a scenario I created for you. You're in the middle of a fight. You're running low on ammo, and you want to get a supply at location A, but you're also at a location that so you're here, for example, you're under a cover, and you want to go to a location A to get ammo, and you want to go to another location B to get a health. And then also you want to have an enemy here that you want to kill. So what would you do first, considering all the situation you have? So that might be actually what you encountered in a real time, in a real life, that you want to make some decisions and examine all the conditions you have. Then how would you do? Normally, you would want to see, okay, how many ammos you have left? Is it enough to kill the enemies, or is the enemy's power enough to kill me with my current health, or how's my skill level so that I can maybe dodge a bullet or so that I can just simply end the game? Well, to actually do it in the AI, you might actually do the same thing to your AI agent by calculating these something called desirability, basically quantify them into numbers so that you can compare which one you want to go for better. So here we can take advantage of the heuristic and the evaluation function again. So here are some basic simple examples I want to show just to illustrate the idea that the desirability of getting a health potion could be inversely proportional to the distance to the location, and is proportional to how many health you have left or you need to restore times a small factor of k. The k basically is a hyperparameter for you to define how the desirability you want. Or the desirability to attack is also something simple like a total strength times the total health, which higher the health or higher the strength of your weapons will increase this desirability of this certain action. So in your brain, when you're trying to make your AI to do certain actions, you can try to calculate these important factors that determines your action decisions to see which one you want to do the next. Depending on how much desire you want to go for health, if your agent is actually kind of timid or is rather playing safe, then this K will be much higher than this K at the bottom of the attack. So very likely we'll try to go get a health potion, even though it can actually kill the enemies without it. So, or you can actually have the enemies go for a style that more violence, and then going for the attack, regardless how much health it's having. So that's something you can incorporate in your AI logics when you're trying to design the AI that's suitable for your game. So above and beyond, there's a lot other to cover. Here's is also something called planner decision planning, which takes a lot more time than just a behavior tree, which is what it does. It will essentially trying to find a feasible plan in the future for the agent. So it's a long-term thing that the agent will trying to execute in a long time of like few turns or how many takes that you want to define. So it's very useful if you want to, for example, design a sniper that will trying to precisely measure the location of the player and trying to hit the player with that one bullet. Then it will take longer to plan than a simple than like a normal AI enemies that just trying to that needs to react in a fast manner. And here you also have other AI strategies to, for example, play chess with the others. So the opponent will trying to simulate what you will do the next turn to get the best result of its action. So that is more related, called the minimax methods and the Monte Carlo. If you're interested, you can always go for that and do some research on that. So here I have some case studies I want to essentially talk about, but due to the time constraints, I will just quickly skip some of the case study I prepared. So one thing I want to talk about here is very interesting phenomenon that happened in the history of the AI, is that tougher enemies will tend to be more intelligent, with quotation mark. Just like the Dark Souls. For the play test, during the play testing, the play tester, this is the result from the play tester, that a weak enemy play test is too easy. So 20% of people think it's not really intelligent. But for a tough enemy playtest, none of them think it's very easy, and so increasing amount of percentage people thinking it's very intelligent, even though actually, when you think about in a Dark Souls game, it doesn't really have any sort of intelligence, because it's being spawned at the right at the same position all the time. It's the same amount of enemies, and the enemy doesn't do much about playing strategies, but attacking you relentlessly in a very fierce manner. So that's a very interesting thing you can think about, that when you're trying to design your own AIs, because sometimes it can actually play a very interesting effect on not a very intelligent AI would appear to be more intelligent in players' eyes. And here are some things that you can actually increase the difficulties in Dark Souls. And the second one is the BioShock Infinite Elizabeth. Some of you might not have played this game, so to quickly introduce this game, basically, Elizabeth is a character that you need to protect. She basically doesn't have much power to fight, and so she will try to accompany you throughout the journey. And it's a shooting game, so you will be using guns and shooting enemies, and she will be trying to avoid conflict, and sometimes you need to protect her and fight enemies for her. And going through this world and explore the storyline. So basically, that's something for a player that you need to protect, and this game did a really great job that make you feel connections and related to Elizabeth, so that you want to actually protect her. Um, but well, if you actually think, but thinking this way, if you think a player, if you're thinking the AI you're spending a long time with is actually annoying, then why would you want to actually protect her? And then most of the game mechanics around this kind of gameplay is become meaningless. And so for players to go through. And another smart things it does is it will try to in battle it's trying to stay out of the sight, and it will try to help the player trying to like pick up coins, and here in the image is passing player a gun to when you're running low on ammo. So often in games you'll find that okay, you're in a very desperate situation that you really don't have any ammos to fight. So that's when she comes in, and she will help you in the last minute to make you feel like, okay, to feel grateful and to feel like she's actually looking after your fight and trying to help in some ways. And some other details is she actually has some emotional system which will show different emotions towards different objects. And even after battle, she will feel relieved, and she will feel sad for people you've killed sometimes, to first give you a hint that it's end of the battle, no more enemies, and also to give you a sense of that, okay, she's just a girl that will also feel something about uh, people in the other people in the world, so to make the game feel more realistic. And the last one is about alien isolation. Is the cheat or not cheat as a question. Basically, what it means is how much should you allow your AI to cheat? One way is that okay, one way you want to we always discuss is that the game uh, the AI might always know your location, but you don't know the enemy's location, so it's not fair. Uh, so should that happen? Should that happen, or should that happen often, or how, to what extent should that happen? That is often a question in game design. So an example in Alien is that in this game they actually have they use a behavior tree for the aliens itself, exomorph itself, to control the behavior when it's attacking players or an attack players. But the AI itself, the exomorph, does not actually know where the player is. So that actually gave a fair start point when you are trying to dodge and playing hide seek with the AI. But it actually has another director AI, a higher level AI for the pacing control, to generally direct the axomorph to the location of the player, but it doesn't actually tell where the player is. So to some extent, it's kind of cheating to helping the axomorph to find your general location, but at the same time, you also have a chance. You also have a fair ground, standing ground, that you don't. The AI doesn't actually know where your location, so it has to find. So you can actually dodge or outsmart it in some ways. And another thing is related to this. It's also behind the scene that uh, in that game you will often encounter something like the AI, the exomorph is going above you or beneath you through the venting system, so it will produce some sound, and to actually make you think that it's actually going through a complex venting system. But actually, behind the thing is not. There's really no real vent. When when the exomorphs go above the leave the scene and go into the vent, basically uh, it's just the object that has all the colliders and the rendering disabled. And then when it's going to the next location, basically it's just a direct path from one location to the other. To think this way is actually just going through you when you're in the game. It's going through you without you knowing it, and then it will show up in the next location with and re-enable its rendering and re-enable its collider, and then coming down from the venting. So that's but in the real life, you don't really know that, and you will think it's actually going through the venting machine, not venting, venting system to make the game fair, but actually it's not. So pretty much then that's also a question I leave you guys to think if you really, how much mechanics you want, how much you want your AI to cheat and to produce a more immersive environment for the player. Uh, because on the other hand, imagine if the AI is not really directed by this director AI, then it might go really off the map to somewhere that's really far from you and trying to search for you without knowing you. So that might be something you don't want in your scary or horror games because you do want everything happen around the player. So that's pretty much all about the talk today. So the last questions is to the players and to you guys is, do players really want smart AI? And that's often a myth to some people because they always think that smarter the better because they keep swearing at the AIs in the game that they're not smart enough, or they think the game is too easy because the AI is too smart. But what would happen if the AI is really smart and starting to outsmart you in some ways? Would you really want that? And if that's not the case, how would you really choose to design your AI in some ways so that it will become more entertained to the players? So that's it. Any questions?